is about radian measurement. It is a measurement that was invented in mathematics for rotation. Now let's have a look at this. If I move my arm from here to there, it's 90 degrees. No? If I go like this and I turn my back to you, you know it's 180. And if I turn from here right around, it is 360 degrees. That's what you used to do at school. Now we're just going to use radians. So as I wrote on the board here, 180 is going to be pi radians, or in today's measurements, you all have calculators, 3.14 radians, and 360 is 2 pi radians. Alright, so mathematicians defined a radian as this term, that amount, where this is an arc, it's a length of s, and you all know there's a center of a circle, and obviously the two radii are the same in this case, they are always. So we find that if this arc is the same as the 2 radians, then this radii, then this is a turn of 1 radian. Now, we all know that if we have an equilateral triangle, the angle is equal to 60 degrees. Each angle is 60 degrees. Now, if this arc must be the same as the radius, we will have to, it will be slightly smaller than 60. So the turn of 1 radian is slightly smaller than 60 degrees. So let's just look at this. If I turn through 1 radian, we know S is equal to R, so S is equal to R, and this is 1 radian turn. So now I turn it through 2 radians. Now this and that's the same, so this is 2R, because that's and that's the same, so it's 2R. If I now turn 1 radian, 2 radians, 3 radians, then I see 1, 2, 3. S is 3 R's, so it's 3 radians. So what we see is that the angle actually in radians is S upon R. S upon R is 2, S upon R is 1, S upon R is 3. This is a circle, you did that at school, and everybody remembers a circle, it's a full revolution, so it's 360 degrees. So we saw that S, the length of the arc, divided by the radius of the circle is pi, it was radians. It was 1 radian or 2 radian or 3 radian, depending on how big the S was. Now if we go around the circle, the circumference of the circle is 2 pi r. And if we want to get the radians, according to this formula, we divide by r and we see it's 2 pi. Now all of you know a circle is 360, so 360 is the same as 2 pi. And 1 pi will then be 180 degrees, okay? So 3.14 radians is pi radians. We then get the formula that the arc length divided by the radius of the circle is theta, or in this case, angle in radians is theta, alright? So we can change it to S is theta r. And we have come to the conclusion that pi radians is 180. So this is 3.14 radians is 180. So what is 1 radian? 1 radian will then be 180 divided by pi to get 1, and we get it 57.3 degrees. So as we said in the beginning, it's slightly smaller than 60 degrees. One of the most important things that you must be able to do is to go from degrees to radians and to go from radians to degrees. Now, how do we do that? So say I tell you the angle is 60 degrees. How are you going to know how much is that in radian? So we know that pi radian is equivalent to 180 degrees. So if I say pi over 180 and I divide it by 1, then it means so many radians per 1 degree. Because this is radians per degree, I divide it in, it's so many radians per 1 degree. Okay? So if you know how much is 1 degree, then 60 will be 60 times pi over 180. It's pi over 3 radians, or in today's language, 1,05 radian. 05 radian. Let's take the other one. If you have 3 radians, how much will that now be, or how many degrees are 3 radians? So if we look at 180 is equivalent to 1 radian, so this means 180 degrees per radian. Okay, so if you divide it, it means how many degrees per 1 radian. But I have 3 radians. This tells me 1 radian, so I say 3 times 180 over pi, I get 171.9 degrees. Now what is important is to remember that when you do any of the formulas, like the formula we've just had now, S is theta r, and you're going to use it in a sum, then you must have your calculator on radians. One thing I want to say that is very important, if S upon R is the radians, we see this is for, say it's meters and this is meters, then we see that radian hasn't got the measurement. It is without any units. And that makes it very practical for us because we can say it's seconds or it's minutes or whatever, especially if you do trig graphs. I'll do 4 sums just to help you to see what can you be asked in radians. So the first formula we did was S is theta r, where theta is in radian measurement. So if you are given a circle, and the question is, okay, what is the length of the arc? And they give you the angle in degrees. You can't work in degrees because all the formulas, there's 2 more, I will talk about them later, you have to use radians. For these formulas to work, you have to use radians. So if you have 70 degrees, you're going to times it with pi over 180 to get the amount of radians. It's 1.22. And then you times it by the radius, in this case, which is 5. And you get that the arc is 6.1 centimeter. I'll do one more where you're finding S, because it is important that when you work with these formulas, your calculator is actually on radians. Now have a look. We give you a circle and we say the radius of the circle is 5 centimeter, and that's a chord. Now you should have learned at school that if a line is drawn perpendicular from the center of the circle, is drawn perpendicular on a chord, say the chord is 8 centimeter, it will bisect the chord. So each one is 4 and 4. Now if we want to get S, we have R, but we do not have the theta in radians here. So we have a problem. So what we do, we go back to our trigonometry. We see these 2 triangles are congruent. So these 2 angles are the same. The whole angle obviously subtends the arc, so this is the angle I'm looking for. That is theta in radians. So half of it is theta divided by 2. If we look in this triangle, we see we have the opposite side and the hypotenuse. So sine of an angle, that is the ratio, input, output. So if you want to work like this, your calculator must be in radians. So now we say, the inverse function, we want now the angle back, so we say arc sine of this ratio is that angle. Or you use this notation nowadays, is theta upon 2. So now we have, this is our ratio, so we say arc sin of that, and we get this from your calculator, which is now in radians. I just want to explain, you all have a different calculator. There is a thing that where it says degrees or radians. So if you work in this radians, where anything you do in circles and you're using any of these 3 formulas, your calculator must be set on radians, because you're going to use sine and arc sine, and you must then get an angle in radians, not in degrees, otherwise it's going to be wrong, because everything has been defined with theta in mind, theta in radians. Okay, so we get that is now in radians, but theta is now this whole angle, so it's twice that. So we see that our radian of this angle is 1.854. So S is theta r, we times it with the length of the radius, and we see that the arc is 9.27 centimeters. So let me ask you a question now. Say you have a clock on the wall, and the minute hand goes from 12 to 4. Okay, so it's been 20 minutes. And the radius of the clock, let's say it's 10 centimeters. How far did the hand of the clock go? Now you can solve that now, because we have the formula, the arc length is theta times r, where theta is in radians. Now let's think about it. That is 20 minutes, so 20 minutes is 1/3 of an hour. But we can't work in degrees now or in hours. We have to work in radians. So we know that a full circle is 2 pi radians. So let's just take a third of that. Then we have the angle that this clock is moving through in radians. And then we times it with a radius, which is 10. So we see the clock actually goes to moves 20.9 centimeters. This is something which actually mechanical engineers use a lot, but you know about it when you were a small child. Remember this merry-go-round you had? You never stood in the middle, you always stood there on the outside because you wanted to go fast. Now let's look at, this is our formula. So if we say distance divided by time, we get the speed. So if we divide that by t, we must divide this by t. Now in mechanical engineering, when you move around in a rotational thing, rotational velocity, then we express it as radians per second, which actually makes quite a lot of sense. So you can see that when your radius is big, that's why you stand on the outside. Some people put a plank there so that it can go really fast, because the speed will then be really fast. I've been focusing quite a lot on this formula, but in your radians section, you will have also the area of a sector. There's your formula. So this is a sector, and then this is what we call a segment of a circle, and the area of that is a half r squared theta minus sine of theta, where that theta is the angle that subtends. So we talk about the segment, that will now be theta, and then you must work out what that is. So when we work with civil engineers, which work a lot with water, it's a very popular question to ask how much water is in this canal, the volume of the water. And because now you have to know the area of the segment and you have to know the length of the canal. I really hope you enjoy working out your radian problems on the card. I saw that the quote on the card was actually on courage. So by Mark Twain, he said that courage is not the absence of fear, but the mastery of fear. Now for young people, for me, courage is very important. Because when you have courage, you can actually try new things and you can cope with challenges in life.